The fluid catalytical cracker, the CAT, or the FCC as it is most commonly known as, is usually the most important process unit in a North American oil refinery since it converts relatively lower value heavier oils into much more valuable gasoline. In fact, the FCC is so important to most refineries that they simply wouldn't be economically feasible without one. Aggreko sales reps should never lose sight of that fact. FCC feed comes from the heavier portion of crude oil. It is the bottom cut on the crude unit and is called atmospheric gas oil. Atmospheric because the crude tower runs at atmospheric pressure. Gas oil because it feels quite oily if you touch it. Since one can only heat crude oil to a certain point at atmospheric pressure before it cracks into gaseous products, the bottoms of the crude tower must be further fractionated in a vacuum tower under a vacuum to reduce its boiling temperature. The vacuum tower produces both a light vacuum gas oil, LVGO, and heavy vacuum gas oil, HVGO. These two streams are combined together with AGO and form the total feed to the FCC. Ultimately, the FCC produces gasoline, propane and butane, propylene, butylene, and cycle oils. Gasoline produced in the FCC is of excellent quality and has an octane in the 95 range, ready for blending directly into the gasoline pool. Isobutane and butylenes are fed to an alkylation unit where those molecules are combined together to form a C8 alkylate material which has a high octane value. It is important to understand that the alkylation unit is entirely dependent upon the operation of the FCC. Cycle oils and slurry produced in the FCC are lower value materials that are eventually blended into fuel oils. At a high level, the FCC unit consists of a reactor regenerator and product separation section. In the reaction section, hot catalyst with a consistency similar to sand at 1400 degrees Fahrenheit is contacted with FCC feed at 600 degrees Fahrenheit in the riser, instantly vaporizing the feed material. The actual reaction takes place at about 985 degrees Fahrenheit over a few seconds as the material moves rapidly through the riser and into the reaction vessel. Surprisingly, there is actually little reaction occurring in the reactor vessel, since for practical purposes it all occurs in the riser. In reality, the reactor vessel is a disengagement vessel that principally exists to separate the sand-like catalyst from the gaseous reactor products. Disengagement is achieved by several cyclones that rapidly swirl the vapor so that the catalyst can drop out from the product vapor material. As one can probably imagine, material erosion is a common reactor problem due to the high velocities encountered. During the reaction, the catalyst is coated with a carbon material commonly referred to as coke. In order to be effective, this coke material must be burned off before the catalyst can be reused. For that reason, there is a slide valve that allows catalyst that has accumulated in the reactor to flow back to the regenerator. The purpose of the regenerator is to burn the coke off the catalyst. Air is blown into the vessel. When it contacts the hot catalyst, it burns the coke on the catalyst to carbon dioxide, effectively restoring the catalyst activity back to normal. Typical regenerator temperatures are near 1400 degrees Fahrenheit, which means that the regenerator requires special metallurgy. As ambient temperatures rise during the summer, the density of air decreases, which means that the mass of air entering the regenerator also decreases. That's because air blowers are volumetric machines. For many refineries, the main FCC limitation is air blower capacity. This limitation is aggravated by the higher summertime temperatures. While especially painful for refiners, it presents a great opportunity for Aggreko, since we can provide additional cooling to reduce air temperature and increase air mass flow into the regenerator. That's the reactor regenerator. On the other hand, the separation portion of the facility consists of a main fractionator, wet gas compressor, and gas processing columns that exist solely to separate the various products. The main fractionator is a distillation column that is quite similar to a crude tower, complete with multiple product draws and pump rounds. Feed enters at the bottom of the tower at about 985 degrees Fahrenheit and then is rapidly cooled to 650 degrees Fahrenheit. Unlike standard distillation columns, there is no reboiler since the feed material enters the column so hot. One significant problem in the bottom of the FCC main fractionator is erosion due to entrained catalyst in the vapor feed. Main fractionator pump rounds exist to simultaneously remove heat at various points in the tower and also to heat FCC feed. Products from the FCC main fractionator are the light cycle oil, LCO, heavy cycle oil, HCO, and slurry, or what is often called decant oil. All these products exchange heat with FCC feed and are further cooled against water before going to storage. FCC overheads is cooled in a series of exchangers, including air fin fans. Gas leaving the reflux drum is compressed in the wet gas compressor before being further processed in the FCC gas concentration unit. Condensed liquid in the reflux drum is unstabilized gasoline. A portion of this material is used as column reflux, while the remainder is sent to the FCC gas concentration unit for further processing. The next video in this series, the FCC gas concentration unit, or the FCC unsat gas plant as it is commonly called, details how gasoline, propane, butane, and fuel gas are separated from one another.